Welcome back. Welcome to the session on dynamic programming. Dynamic programming is a pretty advanced programming concept. In this section, we are going to do hands-on dynamic programming. So how this session is going to be run, it is not going to be a PowerPoint based session. We are going to get into real hands-on dynamic programming in a very short time. I'll take you through a lot of examples and do a step-by-step walkthrough as to how do we approach dynamic programming. That's the way we'll solve it. I'll be using Java as the language, but I think pretty much it's portable to any other language. The core focus will be on the concepts. Before we start with dynamic programming, I think the expectation is students are good with programming, basic programming concepts. They are really good with loops, strings, arrays. So these concepts are really critical before you get into dynamic programming. So a question would not come as solve this using dynamic programming. Whenever you see that the input size is very large, whenever you see that the problems are repeating, then you go for dynamic programming. Anyway, when you go through this entire module, you will understand what is dynamic programming, when do you apply dynamic programming. The focus is get into a programmer's mind to see how he or she approaches a dynamic programming problem and solve a lot of problems. Let's get started with that. So first one we'll take is a very simple problem, a Fibonacci. I think this question is pretty common to everyone. All of you would understand what is Fibonacci, right? So for nth term, it is the sum of the previous two terms. For example, here in this, the third term is 1 and it is the sum of 0 and 1. Fourth term is the sum of second and third. Fifth term is the sum of third and fourth. Sixth is fourth and fifth. That's how Fibonacci series works. So let's get into it. How do you solve a Fibonacci, right? So there are multiple solutions available. You can go for a simple iterative solution, but I've taken a brute force or a recursive algorithm here, right? So a simple solution where we take Fibonacci of a number, you recursively call the number -1 and number -2, right? When you add these two, you get the Fibonacci of any given number. This is a simple recursive solution. Now what happens in this is, if you look at n less than or equal to 1, that's called as the base case in any recursion, because if you don't have a base case, it can go for infinite recursion. So we need a base case to say that, okay, hey, if it hits this, stop the recursion from going further. Now let's look at this time complexity of this particular algorithm. It's kind of pretty bad. It's order of 2 power n. So if at all you give n value as 50, right, it takes so many cycles, a huge number of cycles. If you try this in online GDB, you will see that it hangs for a long time. Let's look at that quickly. So let's look at this solution in brute force algorithm. So I'll give the input. So here you have the Fibonacci that we looked at. So I'm getting a number and calling this particular function, right, recursively. Let's take this algorithm. I'll first give for a small number, say 5. Answer should be 5. It's immediate. You'll see the 2 power n algorithm hanging for some time. Let's take 10. You won't see a lag now. For 10, it's immediate. Let's take 40. You'll see a slight lag when it comes to 40. You see that it took some time. Let me take 43. So there is a lag and answer comes. If I do 50, right, so you would see that it takes a long time to come. The answer is not coming because recursively it's calculating that. And this is the problem with brute force algorithms. Of course, for Fibonacci, we have an iterative algorithm which doesn't take so much time. But when we approach real life problems, you would see that you would go for recursion. It takes a longer time. That's when DP comes in. A dynamic programming is used to solve the problem when it takes a long time, right? Here, we'll talk about two major concepts here: optimal substructure, repeating sequences. We will look at that immediately after this. As of now, I just want you to understand that the same algorithm which was working for a smaller number was working fine, but when the number increases, it takes a long time to come up with a solution. In this case, I don't know how many minutes it would take to come up with a solution. We'll stop it here, right? So let's get back to what we were discussing earlier. So for Fibonacci of 50, you saw that it took a long time, right? And it has to run so many cycles. So it would definitely take a lot more minutes to get to the answer. So what is happening is when you do a Fibonacci of 7, right? You see that Fibonacci of 7 is Fibonacci of 6 plus Fibonacci of 5. Fibonacci of 6 is Fibonacci of 5 plus Fibonacci of 4. Fibonacci of 5 is Fibonacci 4 plus 3. Fibonacci 4 is 3 plus 2. 3 is 2 plus 1, and you get to the answer, right? So that's how these Fibonacci are calculated. Now if you look at it, there is a tree here for Fibonacci of 5 and the same tree is here. So once if you have calculated, ideally we should be able to reuse it, right? That's the way it should work. But when you do a 2 power 50, you can imagine how big the tree would be and how many repeating sequences would be there. So this repeating sequence is called as a subproblem. So if you have a subproblem that is there, right, in this particular problem, you see that 5 is repeating multiple times and you are breaking down the trees to call recursively and find the answer. So if it repeats like this, ideally this is a case for dynamic programming. Whenever you see that there is a subproblem or a substructure that you can actually replace, right, you can calculate it once and reuse it, then you can use dynamic programming. Dynamic programming would dynamically cut down or drastically cut down the amount of time it takes to solve the problem, because it will cut down the tree that is there. So once it calculates for 5, it will reuse it in the other places, so it doesn't have to recalculate it again. If you look at 4 here, there are 3 places 4 is there, 1, 2, 3. So if at all the answer is calculated here, then this tree is not at all required. It will call for Fibonacci of 4. You will already have the answer and you can use it. And here again, this tree is not required. It can reuse the answer. So that's the advantage of dynamic programming. So dynamic programming has two major approaches, right? Both get you to the solution. One is called memoization, which is a recursive approach, a top-down approach. Second is tabulation, which is a bottom-up approach, iterative approach. In this particular video section, in the next 1 hour, we will be looking at tabulation as the approach. I'll take memoization as a separate topic. Right now, the focus is going to be tabulation. Tabulation is an iterative approach. It is a bottom-up approach. We will look at that immediately now. So let's take the same problem of Fibonacci, right? And as I said, right, you get to 1, you have to use the previous 2 terms to get to the nth term of a number. So let's build a table, right? So for example, we'll have the base case as 0 and 1. For a tabulation, you use a table or an array. So you build the array from the base. That's why it's called as a bottom-up approach. You build the next term using the previous 2 terms. So first we'll initialize it with the 0 and 1 index. For that we'll initialize the values. Now to calculate the second index value, we know that it is the sum of 0 and 1. So that comes here. The next value is again 1 and 1. You add up to get 2. You add 2 and 1, you get 3. You add 2 and 3, you get 5. This is how you get to the value, right, that you want. So once you have built this table, right, so for example, the user has given a value of 50. You build this table up to 50th term. You will have an array which has 51 indices, right, and 1 for the 0, and up to 50 you build this table, and then you can return the value of 50. And next time the same user calls, right, saying 50, I need 45. Then immediately you can take from the index 45 and return the answer. That would be the Fibonacci of 45. You don't have to recalculate the value. That's the biggest advantage of dynamic programming. Here you're building up bottom up from 0th, you're building it up, and that's why it's called as a bottom up approach. So how we approach dynamic programming is, first thing is, even before, this is a very simple problem. We know that we have to add the previous 2 terms to get the current term, right? That's a very straightforward one. But usually it is not that straightforward. In the same session, we will see at least some 8 to 9 dynamic programming problems. You will see that the algorithm is not straightforward. So we'll have to calculate, we have to work out the algorithm, and we need to find it. So how we do it is, we actually first create something called as an end state table. So what is an end state table? The end state table is something like, what do I think the answer is? First I'll build the table manually using a paper and pen and find out how the answer is arrived at. And when you create that end state table, you will see that automatically the algorithm comes to you, and that's what needs to be coded. So let's look at what's happening here, right? So in this particular problem, it is pretty straightforward. There is nothing much here. We know that the Fibonacci series is the sum of the previous 2 elements. So you would not see much of a difference, right? So I'll run it pretty fast. So here you build this table. This is the end state table, right? And when you build it, you know that for a particular term, it is the sum of the previous two terms. So we have created it manually, and the algorithm is also very clear to us. And it is the previous element you take. We have the previous two elements sum is the current term sum. So it is very simple solution that we have here. So if you look at Fibonacci of 5, it will give you the fifth element, right? So this is the fifth element. You return the element and that's the answer. So Fibonacci of 4, you directly take this element. So once you build the array once, you can return the answer without rebuilding that again and again. That's the biggest advantage of tabulation dynamic programming approach. So let's write the first program. I'll use java.util.star public class main. I'm going to build the solution here. So public static void main string args. And now I'll have first is we need to get the number. So I'm going to first use the scanner class to get the number. So now we've got the number. I need to calculate the Fibonacci. So for that, we need to first allocate the array, right? So we'll call it the DP or dynamic programming array, new of int of n plus 1. As I said, if you need it for n, you need to build the array for n plus 1. So now we initialize the base elements of the array. As I said, dp of 0 is 0, dp of 1 is 1. This is how you initialize the array. Now you go on building the next element. So I is equal to 2, I less than or equal to n, plus plus I. We'll say that a of I plus I equal to a of I minus 1 plus a of, dp of I is equal to dp of I minus 1 plus dp of I minus 2. So if you have done this, once it traverses the entire array, you will have the dynamic programming array built. Now for any value n, right? So dp of n, if you print this, you will get the answer. Let's run this program. So it's waiting for a number. Let me take 50 itself here. If you see, immediately you will get the answer. Actually for 50 it is showing a negative number because it's exceeded the limit. So I'll take say 30. You will see it. If I change it to long for 50, it should work, right? So this is how it works. The advantage here is if you give any other number, right? So if I give system.out.println 30, system.out.println 15, right? So once it has built, let's assume I'm giving a value of 35. I'll run this program. I've built for 35. Immediately it will give the next two values. So you can easily get the answer for the next two values. Directly you can give that value. So I can just take the array index, that will be the answer for it. So if I've calculated for 35, 30 and 15, I don't have to recalculate. Immediately I'll get the answer, right? This is the biggest advantage of dynamic programming, the ability to reuse that value once you have built it. Here you have built the DP array. Once you have built it, after this, you can call it and use it any number of times till the program ends, and you will get it in an order of 1 complexity. That means immediately you will get the answer. So this is the dynamic programming advantage. So if you look at the time complexity, the time to build initially is pretty high in dynamic programming. It is a one-time effort. After that, you will be able to reuse it any number of times. But in case of a normal algorithm, right, if you go for a for loop based normal algorithm, it is standard linear order of n. If you need for 10, Fibonacci of 10, you need to run it for I equal to 1, I less than or equal to 10. And if you again want it for 15, you have to start it from 1 and start to 15. If you want it for 30, you have to again another loop for 1 is equal to 30. But here, if you have built it for 30, 15, 10, all these things will already be in the array. You can just take the value and return it back. This is the advantage of dynamic programming, right? So now for a quick summary of it is, first is with the tabulation approach, we build a table or an array with the expected value of n plus 1. And then the first value we usually initialize with a 0 or a null. Then we visualize the end table. You will understand the significance of it when we move to the second or third problem. For now, assume that even without a programming paper and pen, we take it on a paper and pen and then we do this. And we come up with the algorithm through that process, and finally we write the algorithm on paper and pen, right? So next is we'll get the value and we populate the entire array, and then after that you can fetch the answer from the array, right? That's the step that is involved in dynamic programming. Now let's take a couple of other problems. We'll get to the second problem and see how to solve it using dynamic programming. So let's take this problem. You are climbing a staircase. It takes n steps to reach to the top. At any time you can climb 1 or 2 steps. In how many distinct ways you can reach to the top? Let's take this. So for example, if n is equal to 2, answer is 2 because you can do 1 step at a time, one step, that is 2 steps, or directly you can jump to 2 steps. Second thing is, if n is 3, output is 3 because you jump 1 step, or you can jump 1 step and then 2 steps, or you can jump 2 steps and then 1 step. Right, so this is the problem statement given, right? So we can look at multiple algorithms here, but when the value of n is very high, typically normal algorithms fail. That's when your dynamic programming algorithm becomes very, very important for you to build. So let's first build the end state, right? So you have a 0 and a 1, and after that, we know that if you have 2 steps, it is 2. When you have 3 steps, it is 3. When you have 4 steps, we have to calculate it. When you have 5 steps, you have to calculate it, right? So we need to work on that first. Manually, how do I calculate how many steps are there when you can get to, when there are 4 steps in total, how many possible ways are there? So that's the first step. So how do we arrive at it, right? So let's take this. When n is equal to 4, these are the ways in which you can get. You can either do 1 step, 1 step, 1 step and 1 step, or you can do 1 step, 1 step and 2 steps. 1 step, 2 steps and 1 step, and 2 steps and 2 steps, and 2 steps, 1 step and 1 step. So 5 different combinations are there. Now when you look at it, you can reach the 4th step. There are 2 ways to reach the 4th step, right? Either from the 2nd step, you can take 2 steps, or from the 3rd step, you can take 1 step. So this is the clue here, right? Either from the 2nd step, you can take 2 steps, or from the 3rd step, you can take 1 step. So if you take the number of ways you can reach the 2nd step, and you take the number of ways you can reach 3rd step, you add them together, that's your answer, right? So let's look at it. So if at all you want to calculate the steps, number of ways that are there to reach the 4th, then you need to calculate the steps of 3 and steps of 2 and add them. That is, we know the steps of 3 is 3, steps of 2 is 2, you add them, you get steps of 4. Similarly, steps of 5 is steps of 4 and steps of 3. That means there are 4 ways. How many ways are there to get to 4 steps? We know the answer is 5. How many ways are there to get to steps 3? We know the answer is 3. And then hence the answer is 8. So now when you build the end state, you know this is where it is. Now the crux of the algorithm is we captured here. For any step, when you have to get to the 4th step, you can get it from either taking 2 steps from the 2nd step or 1 step from the 3rd step. So your algorithm is already there. Now this algorithm is familiar to us. This is almost the Fibonacci series, right? Fibonacci series is 0, 1, 1. Here it is. You have 0, 1, 2, 3, 5, 8, right? That's the algorithm. So you take, now initialize the values with 0, 1. After that, or 0, 1, 2. These are 3 values you can initialize in the table. After that, any nth term, right? You can just go directly to the index. It is the sum of the previous 2 indices you add it. Very similar to the Fibonacci series that we had earlier, right? It is almost the Fibonacci series. Now, how did we arrive at it? We went through the process of building the end state table. When we did the end state table, we found out that it is coming from the previous steps, some of the previous 2 steps. So that gave us the clue that it is almost similar to the Fibonacci. Now I'm not going to write the algorithm because it is almost very similar to that. We'll get to a different problem, right? We look at a variety of problems so that you understand how do we use dynamic programming. So let's skip this one. We'll go to the next problem, right? Grid traveler. So say that you are a traveler on a 2D grid. you begin on the top left corner and your goal is to travel to the bottom right corner. So you may move only down or right. In how many ways can you travel to the goal from the top left to the bottom right, assuming that the dimensions are m and n? So the question is something like this. You have a start point, you have an end point. Now in this case, there are three ways you can do it. One is from S, you move all the way horizontal, go to E. S, move one step to the right, one step down, one step to the right, or move S to down and then move all the way right. So there are three ways you can do it. So right, right, down, down, right, down, right, right. There are three ways you can do it. Now, how come it's a DP? There is a sub problem here. So when you're looking at a 3 by 3, internally if you see there is a 2 by 3 there. So, and then you go to a 2 by 2 and from there you have a 2 by 1 or 1 by 2 and then you have a 1 by 1. So that's why we say that. So if you know the answer for a 2 by 3, from there you can calculate the 3 by 3. So incrementally you can build the solution here. There is a sub problem for a given problem. That's how you arrive at it. So that's why it's called, we can use dynamic programming here. So overlapping sub problems are available. So let's look at this. Here, what is the overlapping sub problem? So when you look at a 2, 3, from 2, 3, there are two ways you can move. Either you can go to 1, 3, it is going down, or you can go to 2, 2, which is going right. So you move, right? So from 1, 3, you can go to 0, 3, which is an invalid location. We ignore it. Or from 1, 3, you can come to 1, 2, right? Which is here. 1, 2 is here. So from 1, 2, you can go to 0, 2 or 1, 1. So there is one valid path here. Now when you look at it, from 2, 3, you can come to 2, 2. From there you can go to 1, 2 or 2, 1. So from 1, 2, 0, 2, which is invalid, 1, 1 is valid, right, which is the end. So this is the second solution. Third is 2, 2 to 2, 1, and then you come to 1, 1. This is the third solution. So there are three solutions possible for this. That's why answer for grid 2, 3 is 3. So now this is where I've highlighted the answers here for you. So 1, 1, there are three greens here from 2, 3 to reach to 1, 1. These are the possible paths right and down that we have noted down. So now let's look at a brute force algorithm for this. If you give a maze solver here, so you do a very similar to the previous one. Either you can move to the right or you can move down. So if you add these two solutions, you get the overall answer. If answer is 1, 1, you will return 1 because that's the base case that you have reached the solution. That's the base case. Else if it reaches 0, there is no possible path. You would say that you will just return 0 because there is no possible path. Else you will call next row, right? You're going down and then you're finding the answer, or you're going to the right and finding the answer. You sum up both, you'll get the answer. So let's run this algorithm and see how it works. The brute force algorithm. This is not a dynamic programming algorithm. It's a brute force algorithm. So here we have the maze solver. I'm calling with 2, 3. Let me run this one. You'll get the answer as 3 here. I'll change it to 3, 3. For a 3, 3, the answer is 6. So ideally we should get a 6 here. But the problem with the brute force algorithm is if you increase it, right? So I'll take a 6, 6. Slowly you will see that it is slowing down because the number of paths increased, right? Now you see that's easy. I'll make it say 12, 12. So it will start hanging because the number of trees are pretty high. So far it has been fine. I'll do 18, 18. You'll see that it will start hanging. The reason is the number of paths which are there are pretty high. The number of recursive calls it has to make is very, very high. The order of n is very high now. So that's why it's taking such a long time to calculate the answer. If I leave it for some time, it may get the answer, right? But you can understand the complexity. So this is the problem with normal brute force algorithms. Now how do we solve it? We get to dynamic programming. So you saw that for 18, 18, it did get the answer, but it took such a long time to get the answer. And as and when the 18, 18 becomes the 30, 30, probably you'll have to wait for years to get the answer. So that's not the way we want. We'll try to do the same problem using dynamic programming using the tabulation approach. As I said, two approaches are there. One is memorization, one is tabulation. Right now we are doing the tabulation. So let's get to the table and then we'll do it. So as I said, the first step is to build the end state table, right? So when it is like 1, 1, right? This is the cell, you directly have the answer. So there is nothing much to do. So this is 1, 1. We have it in the inverted way because when you talk about 3, 3, it is this, right? So it is 1, 1 is this, 1, 2 is this, 1, 3 is this. So that's why it's showing as inverted. So the lefts are all zeros. Here we fill with zeros because if you recall, we need m plus 1 and n plus 1, right? The array size to be m plus 1 by n plus 1. That's why you see populated with zeros. And we know only when this cell is there, right? Only when the end is there, only that one cell is there. There is only one way to get to that path. So the first value will be 1. So we know that answer. Now there are two cells alone. We know that the answer is 1 again. There is only one path to get from here to here, right? So if you look at it, first thing to arrive is, so this is the input matrix for which from here you will return the answer. This is what is going to hold the answer here, right? So here it is only one path. Again, if for from here, if you look at it, there is only one path, right? So these are all 1. From here, there is only one path moving up. So that is again 1. From here, if you look at it, there are two paths, 1, 2, right? So it will be 2. I'm not worried about the algorithm now. I'm just manually trying to see how it works. From here, if you see, there are 3 paths, 1, 2, 3. So 3. From here, if you look at it, from this position, there is only one path straight. So that is 1. From here, if you are going, there are 3 paths again, 1, 2, and 3, right? So that's why it is 3. From here, it is 6 paths, right? 3 from here and 3 from here. There are 3 possible paths from here and 3 possible paths from here. So if you're coming from here, there are 6 paths. So if you understand this, what I said, from any position, if you want to find, not only from here as well, right? If you look at 2, 2, how many paths are there? It is basically the number of paths from here and the number of paths from here. If you add them up, you get this answer. So it holds true for any cell. So if you have this base value of 1 established, then if you look at the number of paths for here, it is basically the number of paths from here and the number of paths from here. So if you add up these two values, you get this value. If you add up these two values, you get this value. If you add up these two values, you get this value. If you add up these two values, you get this. You add up these two values, you get this. You add up these two values, you get this. You add up these two, you get this. You add up these two 3s, you get the 6. So this can be expanded further as well. Now, when you build the end state table, as I said, you directly get the answer from here. We don't have to think further. Directly we have got the answer how to build the algorithm, right? So for a particular cell, we'll initialize this value as 1. We'll initialize these as zeros. After that, once you have got this, then it is nothing but adding the next value. So let's look at this for a 2, 3. If the user wants, once you have built this, after that the user is asking you, hey, what is the answer for 2, 3? You just go here, you get this value of 3 and then you return this value of 3 because that is 2. And so this is the second row and this is the third column. Directly you get here and get the answer. So if the answer is 3, 2, we know that row 3 is this, index 0, index 1, index 2, index 3, index 0, index 1, index 2. So 3, 2, the number of ways is 2. So once you have built this matrix for 3, 3, if the user asks any value in between, you can directly pick that value from the array and return. So if you have built for 18, 18, if the answer is asked for 16, 16, immediately you can return the value of 16, array of 16, 16 will be the answer. That's the power of dynamic programming. Now, algorithm wise, we already discussed it. So this is the goal, which is going to have only one path. This value comes here. You add up those two. You add up these two, you get this value. You add up these two, you get the 2. You add up these two, you get the 3. So we know this is the way the algorithm has to be built. Right, so now we can go into online GDB and then build the solution. So we'll go to online GDB now. Let's build the solution. First, I need some few things, right? We are going to use I'm going to remove this. So we'll do it in the main function itself instead of having a separate function now. So what we are going to do is we are going to have a long table first, which is what is our grid. Last time we called it DP. Either you call DP or you call table, whichever be the way, it doesn't matter. So we'll call it rows and columns. So first we need to declare what is the number of rows and columns. Let me actually build a sub function, right? That might be the easiest way to do is public static. I'll build a sub function which will return grid traveler. I'll have rows and columns, and here I'll have this long table. This function will return the requested answer, right? So for here, what I'll do first is I'll initialize this to all zeros. So let me use the arrays.fill function to initialize to all zeros. So given that I've done this, I need to use import java.util.arrays. Oops. So I've used this. So now we have filled the arrays, right? Arrays.fill we have used, and ensure that each and every element is now 0. So now our algorithm is like this, right? So what we saw is 1, 1. That cell we are setting it to 1. Now we need a for loop for int I equal to, we'll start from 1 till the number of rows are there plus I. For int j equal to 1, j less than or equal to columns plus j. And then what we are saying, first if it is I is 1 and j is 1, we need to ignore it because that table is already initialized, right? We don't have to initialize. Otherwise, table of I comma j equal to table of, we saw that it is I minus 1 comma j plus table of I comma j minus 1, right? We saw that the sum of these two were the answer for that. And once we have done this, it's very simple. We have the answer available. So any number, right? I'll just, if you give a particular row and column, I'm going to return the table of that rows and that columns, right? So this is what I need to return. So let's do this. So we have the function ready. Let's go to the main function. Main, we'll keep it very simple. So system.out.println, I'm going to call grid traveler of, say, first let's test this base case. It should give us 6. Hopefully there are no errors here. So let's run this one first. Long rows plus 1. Columns plus 1. Let's run this one. Yes, we have got the base case working. I'll also try with 2, 3. Yes, that's working fine as well. Now let's give a big number, say 20, 20, right? A bigger one. You will see that it shouldn't take much time to give you the answer. It's immediate. You saw the difference between the regular brute force algorithm and this one. This is very instant because it has cut down all the recursive calls, right? There are no recursive calls here. Bottom up, we are building this entire thing. So it is pretty simple and you got the answer. Tabulation approach as such is very simple. Whenever you solve a problem, whenever you get a time limit exceeded error, always think that probably there is a dynamic programming solution available for that problem. Always think about that. So we'll at least solve another 5 to 6 programs like that. That way you will get a complete understanding of how dynamic programming works. So let's get to the third problem, CANSUM. Write a function CANSUM with a target sum and numbers that takes in a target sum and an array of numbers as arguments. The function should return a boolean indicating whether or not it is possible to generate the target sum using the numbers from the array. You may use an element of the array as many times as needed. You may assume all input numbers are non-negative. So let's look at the examples to understand this question even more in detail. So first one, 7. Can you form 7 using 5, 3, 4 and 7? Yes, it is true because there are 3 solutions, 3 and 4 and 7. Can you form 7 with 2 and 4? No, you cannot form it. It is false, right? So the given array is this 5, 3, 4, 7, and we are asked to find out if we can form the value 7. So let's first visualize with the end state, right? So what you do is you can form 0, right? If at all the question is asked for 0, you know that yes, the answer is there. So we have created an array with n plus 1 elements. So first element is true, 0 can be formed because for 0 you don't need any element. Can 1 be formed? No, 1 cannot be formed with 5, 3, 4, 7. So we'll mark it as false. Can 2 be formed? No. So 2 cannot be formed. Can 3 be formed? Yes. Can 4 be formed? Yes. Can 5 be formed? Yes. Can 6 be formed? Yes, 6 can be formed with 3 and 3. Right? If you have a 3, you add a 3 to it, 6 can be formed. Can 7 be formed? Yes, because 7 is there. Or you see that 4 is there and you add a 3 to it, you'll get 7. So now we got a rough idea of how to build it, right? So once you build the end state, understand that in dynamic programming, this end state represents the answer for that particular index. So if at all they ask you, can 3 be formed? Directly you should be able to get to this index and then you should say, yeah, it's possible. Can 4 be formed? Yeah, that's possible. Can 5 be formed? Yes, it is possible. Can 6 be formed? Yes, it is possible, right? So how do we get to this answer? So we found that initially we initialized all the values directly, right? We said this is true, this is true, this is true, this is true. And how did we form 6? 6 was the trickiest one because 6 we said you have 3 and to that you add in these values, right? And if you're able to get, that is 6. So how we build the answer is like this. So first we build a table with all false, right? And then the first box we'll set it as true for 0 because 0 can be built without anything. And then we initialize the rest of the values, right? So they have given 3, 4, 5 and 7. Those 4 values we'll set it to true. So that's the very first step, right? Now the thing is for the remaining values that are there, right? So how it works is, okay, we have added from 0, we have added 3, we have added 5, we have added 4, we have added 7, and those we have marked it as true. Then you get to the next element which is true in the table, which is 3. From here you go and add the fifth element. 3 plus 5 is 8, which is outside the table. We don't have to worry about it. 3 plus 3 is 6. Yes, make that 6 as true, right? That's the second step. And then 4 plus 3 is 7. So you add 7 as true as well. So that's how you build this table, right? So once you have built it like this, then you can, the built answer is available. Now for any of it, you can directly return the answer. So if you look at the algorithm we arrived at through this process by building the end state table, right? So now let's look at this one in the code, right? We'll build the code and then we'll see how it works. Let's also check for the other number, right? 7, 2 and 4. So initially everything is false. We are talking about first element is true. And then we are going to mark 2 and 4 as this one. So these two are marked as true, right? Now next what do? We'll go to true 2 and then we'll say that from 2 we'll mark this as true and this as true, correct? So that's the next step. And then we go to 4 and then we mark 6 and 8 as true, right? That's the next step. 8 is outside the table. We don't have to worry about it. And you go to 6, nothing else needs to be done there. So if at all 7 is given, you know that from this table, once you have completed the iteration, 7 is false. So you return false. So with 2 and 4, you cannot form 7. So now let's get to the code and see how to build the algorithm. So let's build the solution. I'll have import java.util. Actually, I'll just need the scanner. Scanner sc is equal to new of scanner of system.n, and I'll take a number sc.nextEnt, and now we need the array. Before that, I'll declare the array. So int dynamic programming equal to new of int of n plus 1. So we've declared the array, and my first step is to get the values from the user plus I dp of I equal to sc.nextEnt, and so we need the target sum as well. So int target sum is equal to sc dot nexted. So I've got the target sum, I've got the array. Now we need a boolean for the answer, right? So we'll keep it as boolean equal to new of boolean of target sum plus 1, correct? So now we have the base setup, right? Now first step is to say answer of 0 equal to true, right? So because the first element we are setting it as true. Now rest of the elements, int I equal to 0, I less than or equal to target sum plus plus I. So we are going one element at a time till the last element, right? And then we are going to say, I think for each element we are going to set the array for I equal to 0, j equal to 0, j less than n plus plus j. So our objective is to take each element in the array that we have and add it to the existing sum. That's what we are going to do. So what we are going to do is, if that element of j equal to true, right? That's the first step. If it is true, and when I add I to that particular element a of j, it is less than or equal to target sum. That is, it does not exceed the array, right? That's all we have to check. If it does not exceed the array limits, then it means that I can set that element to true. So this is the core algorithm. Probably I'll explain it again what we have done here. So what we had to do, we had to take a particular element is true, right? So index 2 is true. That means the 0th index that we had in our array was true, and we saw that for 3, 4, 5, 7, all those 4 elements we had set it to true. So I have to take 3 and then I have to add 3, 4, 5, 7 to that particular number and go to that index and set it to true, right? So I'm taking, this is the one which is running through each and every element in the array. So, and this is going to take each and every addition that I'm going to do. So if answer of j equal to true, answer of I equal to true means that particular index is true, and when I add a of j to that particular number, still it is within the target sum. If that is the case, then I set that index as true. So once we have done this, now I have the array built, and let's take any number the user has given. For that particular target sum, the answer has to be printed, right? I'll say answer of target sum. Let me run this code. Let me see if there is any error. Sorry, it's not ans. Yeah. So if I plus a of j, it's not a, it is dp. Here again it's dp. Let's run the code now. So for 7, let's give the same thing that we had as input. So we are going to have first an n value. So that n is going to give us the number of elements in the array. So I'm going to give 4 elements in the array. And then I'm going to say that the target sum that we have, right? So is 7. And I'm going to give 5, 3, 4, 7. Sorry, I made it wrong. Let me run it again. The value of n is 4, and the 4 elements in the array are 3, 4, 5, 7, and the target sum that I have is 7, which is true. I'll again do it. I'm going to give 2. I'm going to give 2 and 4, and I'm going to give the target sum as 7. It is false. So that works fine. So this is the algorithm. I think you might take some time to get through this. What is happening? Just understand here. We are taking for each and every element in the array. For that element, if it is true, that means that is there. Then you add the remaining elements and set that to true. That's all we are doing here. So that's the core algorithm that we have. Hope it is clear. Let's get on to the next question. So you can try this even for larger numbers, right? For brute force algorithms, it will fail. So here, even if you give, let me give a large number. So I'll take 2, 3, 13 and I give 13,000, some large number, even then it will work immediately. But same thing if you try with the brute force algorithm, you will see that it hangs. There is no solution available. But here you will find that dynamic. So next question we will look at is how sum. The same target sum, but now the thing is we have to give the answer as to whether it is how did we arrive at that sum. It's not just true or false. How did we arrive at the sum, right? And if there is no solution, we have to return null. If there are multiple solutions, we have to return any one of them. So that's the question. So let's look at it. If it is 7, so you return 3 and 4, or if you return 7, either of it is fine, right? So you can return 3 and 4 is the answer for 7, or you return 7 is the answer for 7, it is fine. If you give 8 and 2, 3, 5, 2, 2, 2, 2 is an answer, or 5 and 3 is an answer, that is again fine. If you return 7 and 2, 4, it is null, right? Understand that if it is 0 is the question, it is empty set, and empty set and null are different, right? Null means there is no possible solution. Empty set means it is like even without anything in the set, the answer is achieved. For example, for 0, you don't need any input to be there. So let's look at the solution, right? So here again, when you look at it, you have a solution available for 7. It comes it with, so from 7 you subtract 5, you get 2. From 7 you subtract 4, you get. So there is sub problem available here. That's what we are seeing. So that means we get to dynamic programming to solve the problem. So first I'll show you how it is manually done. So for 0, it is empty set. Whatever we discussed the last time, the very same solution. Only thing here now is however we did for can sum, the same solution will apply for best sum. Only thing is we have to store how did we arrive at that solution. That's the only thing. So now let's first look at it. We have the end state table. So I have it initialized for this as empty, and then we have each of these values initialized that we already saw, 3, 4, 5 and 7 I will initialize. Now we go to the next element in the array, which is 3, and then we start from 3 and then we add 3, 4, 5 and 7 here. So 3 plus 3 is one solution that is there, so we add it, and 4 plus 3 is again 3 plus 4 is another solution, so we have added. So now if you look at it, the entire thing is done. We have the solution available here. Now let's get to the actual code for this, right? So the same code that we had last time with a minor change, because we need to store an array here. Either you can store it as a string array or you can store it as an array list. So that's the solution that we are going to present now. So now that we understand the algorithm, let's get to the code here. So first step is we will get the input from the user. So we will have the scanner class. And then we'll have a variable called n, which is to get the number of inputs which are there. And then we'll get the array. So this is the standard array. I'm not going to call it the DP. This is the input array that we are getting. And now we'll get the inputs from the user. A of I equal to sc dot nextInt. So we have got the input from the user. We have to get the target sum. So I'll get the target sum as well. So now we have got the input from the user, right? So the next step that we have is we need to get in and start with the algorithm, right? So the first thing is we need an array list. That's what we discussed. We need an array list of integers, and let's declare this, and it has to be an array because each one is going to have a solution defined. So we have an array list, an array of array list, right? So, and we'll call this the answer, and this is going to be an array list of integers, right? So that's what is the array list that we are going to have. The size has to be defined. So let me define the size of it. It's going to be target sum plus 1. So we already know why this is being done. So I have an array of array list now. So let's get to this initializing this for I is equal to 0, I less than or equal to target sum plus I. answer of I is equal to new of array list of integer. Fine. So we have initialized that each of the answer element is going to be an array list. So now we are going to add the elements. So this is just creating the initial reference for it. This is actually creating the new array list. Now you can add into this, right? So that's what we have done now. So now let's get to the next part where we are going to take each of the elements for int I is equal to 0, I less than or equal to target sum plus plus I. I'm going to take each and every element in the array list, right? So what we have to do now in the array list, we are going to take every element in the array. So we are going to take the first element in the array and we are going to take the add it, right? So for each and every element, what do we do? So let me go back to the PPT now. So if we go back to the algorithm that we discussed earlier, so we have this array and each array has an array list, right? This is the array list that we have of integers. So what we do is when the iteration is 0, right? That means the first time it goes through, nothing is initialized. What we are going to do is we are just going to have these values. Wherever we have 5 is there, 5 is going to get copied here. 3 is there, 3 is going to get copied here. 4 is there, 4 is going to get copied. 7 is there, 7 is going to be get copied, right? So the I loop is actually going to take each and every element. The J loop is going to take every element here, right? So this is the I loop. The first iteration it is going to go through the array. What it's going to do is when I is 0, all I have to do is to copy these elements here. That's what we are going to do first. So when J is 0, J is less than N. This is the elements in the array, right? So what we are going to do is if I equal to 0, if at all that is the case, this is the first iteration that we have. All we need is in the answer, what we have to do, array of A of J equal dot add A of J. So what does it mean? Hope you understand this statement. So what we have done here is I'll again go back to this one PPT. So this is our answer array. In the answer array that we have, what we have done is A of J, right? J is going to be the index. So when J is 3, right, we are going to add. So when J is 0, we are going to add A of J. That means 5 will get added here, 3 will get added here, 4 will get added here, 7 will get added here. So I is 0 means that is the first iteration we are going through. When that is 0, all we do is when I is 0, we are going to initialize these values of the array. So then what do? We'll check for I equal to 1 and we'll see is it a valid place? No, that's not valid. That means what we'll check if the array list size is 0, right? If it is greater than 0 is what we'll check. So if it is greater than 0, that means there is an element there. So that we need to again add the I. So let's go back here. When it is greater than 0 is what we have to check next. So we'll check here. Else if answer of I dot size is greater than 0. That means it is a valid place. That is from here you have to copy all the elements, right, to the target element. So what we'll have to do is first, even before we enter here, we'll check if I plus A of J is greater than target sum, then we'll ignore it. For example, what it means is say current value of I is 3, right, and A of J is 5, it goes to 8. 8 means it's above the target sum. We can ignore those values, right? We don't have to consider those values. So that's why we'll say continue. So here now that we are here, what we have to do, answer of I plus A of J, right? That means current value of I plus when you add A of J to that element, I am going to add all the elements which are currently there. I am going to do an add all of all the elements in answer of I, right? And then I am going to add this I plus A of J. The other thing I am going to add is the current value of J. Add of A of J. So what we are doing here, if you understand these two statements, what's there, right? Let's go back to the algorithm now. So when size is greater than 0, that means there is at least one element here, right? So 3, 4, 5. What we are doing is when we have 3, when we have reached here, and a of 5 is 5, it means it's going out. That's when we did the continue. I plus a of j is greater than target sum, we said we'll continue. But when I plus a of j is less than that, say for example we are taking 3, right? When j is 1, it is 3. So current value of I has, answer of I has 3, and then I'm adding this a of j, right? And a of j has a value 3. So I'm adding 3 plus 3, so it has to come here. So what we are trying to do is, whatever are the set of elements here, all those elements have to come here, plus we'll add the a of j value, which is 3. So that's what has to happen. So we need to get the value of 3 plus 3, the current value of 3 plus 3, right? Only then you will get 3 and 3 here. So whatever is here in the array list, the entire thing has to get copied here. That's why we do the add all. And then we'll say that a of j is 3. You add that to this. So currently we have only 3, and then we have added a of j, which is 3. That gives the value 6. So in the index 6, this is what we are going to have. Similarly, when we get to 4, right? Current value of index is 4, and then I am going to add a 3. So 4 plus 3 comes here, or 3 plus 4 comes here, right? So that's how we get to the solution of 7. So let's get back to the code that we had. So now that we are here, what we'll check is, okay, now that we have added the elements, right? So 3 plus 3 would be there for 6, and 3 plus 4 would be there for 7. So I'm going to check if I plus a of j equal to target sum. That means we have got the answer, right? So for example, we have got 3 plus 4 and we have got to 7. So if that is the case, all we need to do is to display the answer from the target sum, right? So I'll do for int k equal to 0, k less than answer of target sum dot size, because that's the array list which has the answer, plus plus k system dot out dot print, and let me do use print answer of target sum dot get of k. So this would get us the value of k. I'll just add a space or something here so that we know that between the elements we have it. And once we have printed this, we can return, because in house sum only one solution is required. We don't need all the solutions, right? I'll return from here. That way it is done. So let me run this code. Let's see if it is working fine. Hopefully there are no compilation errors. Nope, there is a compilation error. Cannot file symbol array list. So I'll do a java util dot star instead of java dot util dot array list. For j equal to 0, I need to do int j equal to 0. So I missed that int. Let's add that. Hopefully rest of the logic is fine. Yep, we are in the prompt. Let's go back to the question that we had. We'll use the initial input is 4 elements, that is 3, 4, 5, 7, and the target is 7. So let's see if the solution is coming. Yes, for 7 we are getting 3 and 4 as the answers. Yes, we have got the answer. So let's run again. We'll do for the same 2 elements. We'll give 2 and 4 now, and then we'll see if it can form 7. Nope, there is no solution here. That's why you're not getting anything. So let's do one more thing. We'll say 1, and then we'll do a 2, and then target sum is 10, right? Yes, you're getting 2, 2, 2, 2, 2. So you see that the solution is working fine, right? So hope you understood the algorithm now very clearly. So if you have any questions, add it in the comments. I'll answer it. So the code is here. You can take a look at the code. This is the code to do that, right? So let's save this and we'll move forward. So now that we understand dynamic programming, especially the tabulation method, let's look at a slightly complex problem so that it gives a holistic view of dynamic programming. So there is an ant in an uneven floor. So this question is about the longest distance it can travel within the same room. So let's look at the question. The floor in an uneven n by n room is uneven. Each tile is slightly higher or lower than the other, and it is represented in a 2D array format. There is a small ant which is trying to move across the floor. It wants to travel the longest path that it can. It can start on any tile within the room. It can just climb 1 centimeter at a time. So it cannot jump from a tile which is 6 centimeters to a tile that is 8 centimeters. Assume all tiles are of different height. The ant can never travel between 2 tiles of the same height. Objective: Find the maximum path length, that is starting from any tile in the room, such that all tiles along the path are in increasing order with a difference of 1 and can move in 2 directions from any given cell. It can move to next row, same column, or next column, same row, right? So these are two methods it can move. That means it can move to the right, it can move down. So the input is a floor that is given. For example, 1, 2, 9, 5, 3, 13, 0, 6, 7. So in that, if you look at it, 1, 2, 3 is the longest path that is there. So the output is 3. So here if you look at it, once it reaches 3, from 3 it cannot move to 13, from 3 it cannot move to 6, from 3 it cannot move to 5. So it cannot move to 2 even though there is only one difference, because the ant has to always climb up, it cannot climb down. So that's why the answer is 3. So the room size can be as large as 30 by 30 tiles. So now, so let's look at this input matrix. First we look at the end state visualization. So 10, 11, 12, 20, 7, 33, 13, 21, 34, 35, 37, 22, 101, 102, 103, 44. Now first we'll do something called as an intermediate state visualization, and then we'll go to the end state visualization, because it's difficult to do 2 steps at the same time. You'll understand when I give the intermediate state visualization. So when you look at this right and down, the first one is 1, right? When you just consider this 10, the maximum length it will have is only 1 tile. Now when you look at 10 and 11, there are 2 tiles it can move, so the answer is 2. When you look at 10, 11 and 12, it is 3 tiles it can move, right? So from 12, if you look at it, 10, 11, 12, 3 tiles. Now when you look at 20, right, it is still 1, because I'm just considering this 20 alone. So it is not in a path to move. So only considering this tile, there is only 1 move it can make. 7 is only 1. 33 is again only 1. 13 is 4. When you look at it, 10, 11, 12, 13. So 13 is 4. 21 is 2, because 20 is there. 21 is 2. 35 is 1. 34 is 1. 35 is 2. 37 is 1. 22 is 3, because 20, 21, 22 are there. So this is 3. 101 is 1. 102 is 2. 103 is 3. 44 is 1. Hope all of you understood how we arrived at it. So just considering that, if you consider this cell, this is the longest path, so it is saying this. If you consider this cell alone, it is on its own, there is nothing there. But when we look at the principles of end state table, right, so far we have looked at. So if we are considering only this matrix, right, or if you are considering only this matrix, 10, 11, 7 and 33, this cell of 1, 1 should give the answer of the max value within this table, right? And if we are giving this value here, right, this table which starts at 10, 11, 12 and ends at 37, it should give the maximum path within this table. That's the philosophy of dynamic programming, right? So in this table, when you look at it, so if at all this cell is fine, this cell is fine, here it is fine. But when you come to this cell, if you look at it, this entire row, if you look at it, how do we calculate if this is the input, right? 10, 11, 12 and 20 is the input matrix given. The maximum path is 3, right? That's what should be the answer, 10, 11 and 12. So here, when you are calculating the max value, right, in the end state table, what should happen is 1, 2, 3, and here 3 should come, because when you give this entire row, within this entire row, the maximum value is 3, right? Similarly, when you look at this matrix, right, 10, 11, 7 and 33, the maximum value is 2, because 10 and 11, right? So here the answer 2 should be there. So that's how we'll construct the end state table. So let's look at the end state table now. So here 1, 2, 3, and here the value 3 comes, because if you look at 10, 11, 12 and 20, the maximum value or the longest path is 3. Here it is again 1, because we are looking at these two ones. Here it should be 2, because we are looking at this square, so it is 2. Next is 4, obviously. After this it is 4. So if at all you are giving this table as the input, the answer should come as 4 here, because 10, 11, 12, 13 is there. Next round is going to be 34, 35, 37 is 4 again, because the longest path is 13. and then again 4. After that is 1, 2, 4 and 4. Hope all of you understood why 4 came for 44, because if you are giving this entire table starting from the top left to the bottom right, so if you are giving this entire table, the answer would be 4 for this, right? That's how it has to be calculated. So now can we directly construct this table? Probably yes, but it is much more easier to construct the intermediate table and then do a max of the value and get to the final table, right? This is how it has to be calculated. We can take another matrix and then again do the same exercise, right? So I've done it here for another matrix, right? So here if you look at it, you have 1, 2, 3, 4, 5. So that becomes the longest path. And when you look at this 11, 10, 11, 12, 13, 14, 15, that's what is represented here, right? We can do a few matrices like this and we can calculate the value, right? So you can pause this video and I would say that you can actually, so if you look at this matrix, right, there is no path at all. So the maximum path again would be only 1. So you can pause this video at any time and look at these matrices. Try to calculate the intermediate matrix. Say for example, for this matrix, now is a good time to pause. You can calculate the intermediate state matrix and the end state matrix and then validate the values that I've got on the table here, right? So that's why we have given these examples, and then you can check the answers with us, right? So one more matrix. These are different flavors. Okay, there are some unique test cases within each of these. So you can try it and then you can see if your answer is matching, right? So okay, I'm giving the answers as well. If you want, you can pause it, calculate the answer. Okay, so that's it. So now for the solution, right? So how, when we constructed the intermediate table, if you look at it, we calculated the path within this. If it is 7, next cell when we are calculating, we'll see if these two values, right, this one is higher than this, or if it is higher than this, this value has to be incremented by 1. Again, when we are getting to the third value, how we do it is we take this value and then we will look at 8 and 9. It is increasing, means we'll take this value and increment it by 1. That's the way we have calculated this, right, entire matrix. So the algorithm is like this. So we'll initialize matrix of 1, 1 as 1. And then we'll run it for all the cells here. This is the one. This is the intermediate state construction, right? This is not the final state construction. So how we are doing is, if I plus 1 is less than or equal to n, a of I plus 1 minus a of ij is 1. That means there is one increase in the row. Then matrix of I plus 1 comma j equal to matrix of I comma j plus 1. Similarly, if j plus 1 column is less than or equal to n, then we are checking the column. Within the column, is there an increase? If that is the case, we'll increase the matrix value by 1. So if you do this, the intermediate state values would be calculated. After that, to calculate the final state, the end state table that we did, we are just doing a simple find max. A find max is nothing, a simple method that I've written to calculate within this matrix for this given row, whichever is the maximum value, right? You can write a simple one. A loop which will run from this I till this I and j. It will run the matrix and find the maximum value within that matrix, right? Basically it is doing this part. So if you are giving this I and j, then it will take this matrix and see what is the max. Is it the maximum? Is the maximum? Is the maximum? It will do that and find the maximum. If you give this table, find max method would return 5, right? If you give this matrix, find math method would return 5, right? That's the value. It comes here within that sub matrix, which is the highest value, right? So that's what it returns here. So this is how you calculate the value, the maximum ant path. That's what it returns here, right? You can run this table and then you can find it. So if after you have done this, if they want to give you max matrix of n minus 1 and matrix of n minus 1, if you print, that will give you the final value, right? So now a quick change in the question, right? So here it is the same question as earlier. Only thing is the ant can move in all 4 directions. It is not just right and down. It will move in all 4 directions. So we'll do the intermediate state construction and final state construction. You can work on the algorithm here, right? I'm just taking this example. I'm doing the intermediate state construction here. Now if you look at it here, let's take this, right? 103, 104, 105, 106, 107, right? When you look at it this way, the longest path becomes 5, correct? This is 5 because in the reverse order it is able to go and get to that answer, right? So you can do the final state visualization based on how we did. It's the same find max method. The only thing here is there's a slight change in the algorithm. You have to consider all the 4 directions and calculate it. I'll close it here, right? I'm not going to give the answer. I want you to work on the solution. That way you'll get a lot more confidence and in solving this dynamic programming. So let's understand tabulation again, right? So you have to build a table with size expected value plus 1. If at all it is like a matrix that we have, you have to build it with n plus 1, n plus 1, right? First value would be null or 0. Visualize the end state table, and in case of the matrix that we saw, we have to do the intermediates table and then calculate the end state table, because it is difficult to do directly the end state table, right? That's what we did. Build it with the known values. When you do that exercise, you will automatically know how the algorithm works. So we did this for multiple programs. We in paper and pen, we first calculated the intermediate value. When we did that end state table calculation, right? When we did that, automatically we came to know how the algorithm works, and it was very easy to code that. So any cell, the value would be arrived from the previous cell values, right? So that's how it is. So something to do with it's an incremental build. That's what visualization is all about, or tabulation is all about. Tabulation is about incrementally building the solution. You will get the answer from the previous cell's answer or previous cell's answer, right? Either it is a row, column, or a set of cells in the row and column. That's how the current value cell is arrived at. So always remember that dynamic programming is an incremental algorithm. If you go back and look at the same steps that we have done, if you look at this video again as well, you would clearly understand that how this dynamic programming tabulation approach works. So far what we have looked at is tabulation approach. It is a bottom-up approach. It is an iterative approach, right? That's what we have seen. There is an entirely different approaches for approach available for dynamic programming. That's called memoization, which uses recursion. I'll actually take another video on memoization. If you're comfortable with tabulation, you can continue with this. It is not like in tabulation you cannot do something, and in memoization only you can do something. There is nothing like that. If you're really comfortable with the tabulation approach, you can go with that. But sometimes I've seen that some problems are easier to solve it using recursion and memoization, right? When you find that there is a recursive solution available, if you apply memoization immediately, you will get the answer, right? So with DP approach. So sometimes I've seen that it is very easy to arrive at the memoization approach as well. So we'll look at another question or another video where we will discuss in detail the memoization approach. For now, I'll assume that you've understood the tabulation approach. You can add any questions or comments that you have on this video, right? Add the comments, or any questions you have, add it in the comments. I'll answer those. Thank you.